So for the next video on chapter 28, we're going to talk about resistivity and conductivity, and this is in chapter 28.4 of the textbook. Okay, so we can define electrical conductivity, and we're going to use a lowercase Greek sigma to stand for conductivity. And it's a measure of a material's ability to conduct current. So we've talked about conductors versus insulators. So conductivity is really quantifying what we mean by a conductor and an insulator, because even not all conductors are created equal. Some of them conduct electricity and currents a little bit better than others. So, and we talked before, so we talked about current density, J, which has to be proportional to the electric field E, and this electrical conductivity sigma is the constant of proportionality that defines that relationship. And we can define sigma as this little n. Remember, that's the number density, so that's related to the number of charge carriers we have, times the charge on each charge carrier, E squared, divided by the mass of the electron, since it's the electrons that are carrying the charge. And this TMF is the mean free time between collisions. So remember when we talked about current and how what's actually happening on a microscopic level. So your little electrons are actually bouncing back and forth between the different atoms. And the speed, there's actually a large speed between the collisions, but the collisions happen very frequently. So TMF, so that's the mean free time between each collision. Okay, so that's conductivity. Resistivity is just the reciprocal of the conductivity. So if we want to write that the electric field is equal to the resistivity times the current density J, or that the resistivity rho is just 1 over the conductivity sigma. And generally, the conductivity and the resistivity depend on the temperature, and it's usually a linear relationship, where if, let's just look at the resistivity, so the resistivity at some temperature T is equal to some reference resistivity rho 0 times 1 plus alpha T minus T0, where T0 is some reference temperature, and T is the temperature you're interested in, and alpha is known as the temperature coefficient of resistivity. So in your textbook, page 872, so they have some data for different materials here. So they have this number density little n, so the conductivity, the resistivity, again, remember they're really the same thing, right? They're just reciprocals. And it also has this temperature coefficient of resistivity alpha. One of the interesting things to notice is, well, these values of alpha tend to be pretty small. So unless you have a really huge change in temperature, you usually probably won't notice this. But another interesting thing to notice, alpha is usually positive for conductors. So that means for most conductors, as the temperature goes up, the resistivity goes up. So it's actually harder to conduct electricity. Whereas for semiconductors, so semiconductors, carbon, germanium, silicon, it's usually negative, which actually means for semiconductors, as the temperature goes up, the resistivity goes down. So, and yeah, so for example, so if you look at something like tungsten, so tungsten is a conductor. So, and this is now the resistivity as a function of temperature, and alpha is positive, so it's actually as the temperature goes up, the resistivity goes up. So it's a worse conductor at high temperatures. Whereas for a semiconductor like carbon, so actually it's just the opposite. So as the temperature goes up, the resistivity goes down. So it actually becomes a better conductor at high temperatures.